question. You already know two of the possible question, right? This high frequency and then the pole finding, right? So just study. Now I want to introduce a concept called transit frequency of a transistor. This characterizes what is the maximum frequency a transistor still operates well as an amplifier itself. It's just like you build a building. Your building cannot be stronger than the steel or the brick you use to build the building. So your circuit cannot be faster than the transit frequency of your transistor. If your transit frequency is 100 gigahertz, your circuit is not going to achieve 200 gigahertz. And usually less, you need to have some margin, right? Maybe 40 or 20 gigahertz. Okay, just like the building. Right, you say my building can support maybe 1 ton per meter square. Then your bricks need to maybe at least support 2,000 kg per meter square, right? Otherwise, you cannot do that unless you have some special design. And this is the so-called transit frequency. And what does it mean? It is like we bias the transistor in the AC mode and current mode. We try to apply a current to it and find out the output current. If you still have current gain, then that is good. But when you go to very high frequency, the current gain will start dropping, eventually becomes 1. And that is the point that you call that frequency the transit frequency. A very quick question. Isn't that this is insulator? How come I have currents going into my gate? Now you have capacitor, very good, because now we're talking about AC. Your gate only has infinite resistance if it is DC, like this case. Now you add the capacitor, you have current going in because it is AC. You're charging the capacitors, okay? So transit frequency is the frequency at which I out divided by I in equals to 1, okay? But I also need to say the biasing condition with the V out equal to 0 means I ground it, right? This is V out equal to 0. This is the transit frequency. So I want to find the transit frequency. What should I do? Draw the small signal, right? I start with this, and we are very familiar with the small signal already. This is plus minus VGS. This is GM VGS, and this is the R out. That's it. But then now the point is I need to add the capacitor. I will add all of them. C, G. Yeah, I will do that later. I just draw everything. CGD, CG, S, correct? I also have a CSB, and then here I have the CDB, right? Sorry, sometimes I capitalize, sometimes I don't. But one more thing I need to say. Very good. Here is grounded by definition, right? Because when I find it. And then the input is what? This is the input, I in. And then what I'm trying to find is I out, right? So I want to find what is the relationship between I in and Y out, I out. If I draw this to you, you can solve it in E122 already, just KCL, KVL, right? It's just that you might not know how to do it. Now, the first thing, we are going to simplify it quite a lot. Thank you. Yeah, so I missed this one. If you look at the configuration, source is also grounded, right? Okay, so because you say this, what can we simplify? Because the source is grounded? Yes. CSB is gone because you have ground at both terminals. And here I say ignore channel length modulation. So this one is gone. How about CDB? Again, this is difficult to see, right? I make a lot of mistakes when I was a student. But look at this. The current is not going to go to CDB. Because this point is grounded. I put the arrow here. This is still grounded, right? You are not going to draw any current. Because if you have current going through CDB, this point cannot be grounded, right? So this one is gone. Yeah? And then I told you that ignore CGD. Okay, because it's small, very small overlap. Now here you don't have Miller effect, however. So you only you have this CGD because we're doing this current source. In particular, when you go to high frequency, even voltage gain is very small. You don't have a large Miller effect, right? So these are all gone, right? So then what is I out? Based on KCL, can you tell me what is I out? GMVGS is just that simple. You only have one place to go. I out equals GMVGS, right? What is VGS? No, I mean, yeah. What is VGS? How do you get VGS? Just the potential drop across it, as you say, just the current times the impedance, right? So this is GM I in times impedance, which is J omega. I ignore the phase, right? Just for simplicity. J omega C GS, right? So when omega equal to omega t, which means F equal to Ft, right? At the transit frequency, we know that I out divided by I in equals to 1 by definition, right? So when I out divided by I in equal to 1, just look at here. I out divided by I in equal to 1, then it means omega equal to GM divided by CGS. Okay? So that's it. This is the transit frequency. That is the highest frequency your transistor still considered as useful as an amplifier. And it's very normal. You see, now you understand again why GM is important. If you make GM small, maybe it works well in the channel length modulation or whatever, but you have a very low frequency. It may work well at DC, but you have a very low transit frequency. You also want to reduce CGS. If you can reduce CGS, then your transit frequency will also increase. And that is very natural. If I were the interviewer, I ask you, what is transit frequency? You say you forgot. Fine. No one can always remember. But guess, how is it depends on the transistor parameter? I hope you can at least tell them, well, if you have larger parasitic capacitor, transit frequency will reduce. Almost is a common sense for EE, right? Larger capacitor, lower frequency. But if you can further relate to probably CGS because the gate is the input. I remember when I derived this, it probably CGS. Yeah, it's a good guess, right? Okay. Any questions? So although this is a new concept, but the whole process is just a review of this, how to draw capacitor, parasitic capacitor, and how to solve the KCL, KVL. This is the skill you should have now. Okay. So we are done with these basics. Now let's go back to look at the response of a common source amplifier.